Interstellar travel, the biggest fascination of every young scientist and the staple of science fiction that could well be our reality in a few decades. But how do we build interstellar spacecraft? Are there even habitable planets out there? Join us in today's video as we explore the far-flung concept of interstellar travel. Gone are the days when interstellar travel was a far-flung dream and the main storyline behind every fictional sci-fi novel and blockbuster. But as technology and science have continued to advance, our rockets, space probes, and other spacefaring gadgets have gotten better. Consequently, this has raised the optimism amongst scientists and astronomers that interstellar travel could indeed become a reality. In recent years, we've been introduced to new technologies and concepts that could potentially make this happen. One of them is the theory of the wormhole and the famous Alcubierre warp drive. Interestingly, there's one more, but we'll save that for later in this video. Since humans began to explore space in the 1950s, all our trips to the world beyond have been powered by spaceships, and it's very likely that all our interstellar trips would be powered by the same vehicles. Perhaps we'll only need to improve their technological capability. But to be candid, even the most technologically advanced spacecraft will struggle to facilitate our interstellar dream, especially because we're still restricted by the cosmic speed limit known as the speed of light. In fact, the fastest we've ever traveled using nuclear-powered propellers is 4.5% the speed of light. Of course, that's nowhere near what is required to power our interstellar ambitions. For instance, Alpha Centauri, the closest star system to our planet, is about 4.4 light-years away. The fastest manned space vehicle was the Apollo 10 rocket, which traveled at an incredible speed of 25,000 miles per hour. This is fast enough to complete a one-way trip to Alpha Centauri in around 120,000 years. That certainly is not the type of speed we want. Thankfully, we can reduce this travel time to 44 years if somehow we're able to propel spaceships to move at 10% the speed of light. But due to the problematic rocket equation, we'll need a fuel tank bigger than the entire observable universe to power a traditional rocket at this speed. Critically, we need a fuel option with the maximum energy density. Perhaps the best way to achieve this is to convert resting mass into energy. This takes us back to the famous E=mc² formula. If, for example, we decide to go crazy and blow nukes behind a spacecraft as a way of propelling it, we might just be able to achieve this. But of course, it's not without its problems. Around 34% of the payload capacity of the spacecraft would have been taken up by the 300,000 1-megaton hydrogen bombs needed to facilitate the trip. Actually, this was one of the powertrain options that scientists considered by Freeman Dyson for the Orion project as far back as the 1950s and 1960s. But then again, this method is confronted with many problems as well. Excluding the return trip and other miscellaneous expenses, we don't know how humans will react to being confined to the four walls of a spacecraft for 44 years. More importantly, the 1963 Test Ban Treaty disapproves of the use of nukes and other explosives in space. Another viable option for achieving this is fusion rockets. This can either be done by pulse blasts like the Daedalus project or ongoing fusion. However, the technology for fusion is still developing. As such, fusion technology is only able to convert 1% of rest mass into energy. Well, thankfully, antimatter drives are one option that would most likely get us to 100%. Usually, whenever matter meets antimatter, both elements are eliminated. During this process, all of the remaining mass is converted into energy. This is perhaps the most efficient fuel we could ever get. For perspective, we will only need 10 grams of antimatter to transport us to Mars. And more interestingly, we could get there in a month. However, harvesting and storing antimatter is a whole other problem in itself. In reality, it is very much possible to produce antimatter through particle accelerators like the Large Hadron Collider. However, the process is slow and incredibly expensive. So far, we're able to generate a small number of antiprotons at a time, which is certainly nowhere near the kilograms of antimatter needed to power us to the stars. To get anywhere near the required mass of antimatter, we'll need to increase our antimatter production rate by a factor of 100 trillion. One advantage of this process is that it allows us to generate at least 50 times more energy per kilogram of fuel than the best fusion powertrain option. And generally, low fuel weight means our maximum speed is ultimately limited only by how much antimatter we can generate. Hence, it would be possible to reduce the travel time to Alpha Centauri to 9 years. And with greater efficiency, the traveling time could be reduced even further to less than 4 years. But what if we could transcend to the far corners of the universe using lightsail technology? Would that make us travel faster? Most likely yes, especially since we won't be carrying any fuel on board. With lightsail technology, we should be able to achieve 10% light speed effortlessly. The closest demonstration of this technology is the Oumuamua, which flew past our planet in 2017. Scientists believe the interstellar object has awkward movement and acceleration that suggests it might be powered by a lightsail. Additionally, a few unmanned space probes are powered by lightsail technology. Expectedly, a crewed lightsail spacecraft would no doubt be bigger than Oumuamua and our unmanned spaceships. But other than that, there aren't many problems with using lightsails to power our interstellar travel ambitions. Up next is the black hole drive, an artificial black hole that represents one of the fastest options for interstellar travel. The black hole drive isn't powered by the real-life matter-gulping black hole because it's not made of mass. Instead, it's made from light, and just like light fusion and light sail technology, it offers a super efficient energy density. When concentrated in a small region, the energy density produced by a black hole should be able to bend the fabric of space and time, enough to produce a singularity. At their peaks, such black holes could generate up to 160 petawatts, which is about 10,000 times the world's total power consumption. But which of these systems would get us closer to interstellar travel? First of all, it's important to note that our current space travel technologies are inefficient for facilitating interstellar travel. And as emphasized earlier, powering spacecraft with nukes is not a viable option. That leaves us with a number of streamlined options. On paper, the fusion technology looks like a real viable and sustainable option. If pursued with all tenacity, we could have a working fusion engine in around 50 years from now. This means we might just be able to land on Alpha Centauri sometime in the 2100s. Recently, scientists at NASA's Defense Advanced Research Projects Agency, aka DARPA, accidentally produced a real-life warp drive system that has the ability to travel even faster than light. But as expected, the system must be developed even further before it can be used to transport humans outside our solar system. In the same way, powering spacecraft with antimatter looks like a concept that's way beyond capacity at the moment. With these options ruled out, light sails or solar sails may just be our last resort for traveling beyond the borders of our solar system. It saves us the stress of carrying fuel on board the spacecraft, and more importantly, the technology is a lot easier to develop compared to warp drives. Also, it is more realistic than traveling through hypothetical wormholes. But in any case, scientists will need between 5 and 10 decades to get these technologies to a working stage, at the very least. However, at today's rate of technological development, well, who knows? Visiting Alpha Centauri or some potentially habitable exoplanets wandering the outskirts of our very own galaxy might just be around the corner.